Hi, I'm Tom and I talk about code. Welcome to another Rust programming livestream. Today we're doing more work on my compiler for my programming language, which runs on my own virtual machine. Now, today we have one simple goal, because the last few streams we've started poking around with the internals to optimize the code that we're generating so that it uses registers for values rather than doing everything through the stack, and that has broken array indexing. So we have a really simple code sample here. If I swap to the correct scene, we have a really simple code sample here where we create a variable b, which is a pointer. We point it to some arbitrary memory. We set two values in it, and then we try and return one of those values. If we step over to my little virtual machine playground, which I really should make live. Currently, I don't have a version of this running on the public internet, but maybe by the time this video goes up, I will. So we have the binary that I compiled from that loaded in here. Binaries can be loaded in the URL bar, and we can see all the code. So let me reset this and tick through this program. This is where the main function starts. Okay, let's zoom in even more. No, let's not zoom in even more because then I lose the tick button. Let's zoom into about here. I think this is good. Hold on, let me really optimize the scroll bar placement. Okay, so we can tick through this program. We can kind of see what's happening. We load the constant 1024 in register A with these two instructions, and that's good. And then we store A in a variable, in the first local variable in the stack frame. So this is what we expect, right? This is equivalent to creating a local variable and storing the constant 1024 in it. That sounds good, that sounds good. Then what do? We load 0 into B. Now, we then load the first, so the base pointer, right? The BP register, this is the base pointer. This is something we use to hold on to remember where our stack frame is. And from that, we get the thing that we just saved, right? Base pointer plus 0. We stored there, we now load there into the C register. Now we do this push and pop, and that's a bit weird, so that's almost certainly a bug, but that's okay. This is a little bit redundant. We'll work out where this is going wrong. I thought I fixed all of these, but we'll have to dig a little bit further. So we do a push and a pop, which is silly, and we end up with the C register having the value of the variable, which is great. We shouldn't need to load it again. We should remember that the variable, we just put the value in that register, like up here. But that's okay, we can do a bit of redundancy. What worries me is, immediately after this, we seem to forget that we used the C register for something. So what I think is happening here is the result is not being threaded through properly. Even more than that, it looks like we have an expression that is not properly reporting where it puts its value, because that's the only case this should happen now, I think, unless we have a kind of expression that isn't checking properly. So either we're not, either our expression being compiled, this expression being compiled either isn't reporting that, actually no, this expression, right, part of this statement. So let's have a look at where I've defined this statement. It's in CodeGen block, because obviously I call it block and not function or anything, because, you know, obviously it's actually more specific than a function, right? Because a block is also the thing inside of an if or a while statement. So we have a block, a body, a thing that gets compiled. And if we have a look at assign deref. Okay, so when we assign deref, as in when we say b0 or b something equals 17, we rewrite this. What is going on? Oh, interesting. All right, so we rewrite this as a different kind of statement. We write it as an assigned deref, which is, you know, we dereference something and assign to it, because dereferencing is different on the left-hand side and right-hand side. That's all fine, which is the one immediately after. So we're doing this kind of statement. Now, this looks wrong, because this isn't how we do things anymore. So I actually did miss this. My intuition was right. So this is what we're popping into C. And we're probably going to see a pop into B as well, because of course we do. So we need to handle how compile expression now returns information, because it doesn't give back a compiled thing. It gives back a, let's call it res adder. Okay, and let's call this res value. Except there's a problem here. This state should no longer be this state, it should be the res adder state, the state from the result with the address. Do we use this state again? Do we do a state? No. Okay, that's okay. That's okay. So now we need to know. So we've followed the state through, but we don't just want to put these things in B and C. So we need to tell the state. So res value.state, we're going to say let state equal res value.state. We're going to move out of here and we're going to have it here. And we're going to make this mutable. We're going to say, oh, and also this needs to be res adder and this needs to be res value. So we're passing information out. We're passing information from compile expression about where the stuff ended up. And these results we can say if res adder dot destination, right? If it ended up on the stack. So if these things both ended up on the stack, then this is when we do this pop. Except we don't pop into B and C, we pop into temporary registers. Let's do this. I don't actually know how Rust wants to format this when we have this kind of line break, but I'll leave that up to Rust. That's a Rust problem, not a me problem. Okay, so we need to get two temporaries, right? So we say state.reserve temporaries. We say we need two temporary values while we're working here. We let T0 and T1 equal. We can basically ask for a pair of temporary registers that we're guaranteed to be able to safely work with that will be different. Two different registers, cool. So we do this same bit of work. B, C, T0, T1, cool. I think that's, yeah, that was the right order. Okay, T0, T1. These feel out of order, that's okay. We'll think about that more later. Actually, hold on. Pop B. Pop B. I feel like there's a pop B missing, because that actually shouldn't be there. But anyway. Actually, here's the pop B and pop C. So this is part of the problem. This isn't the full problem. This is part of the problem. But fixing this is going to be good. So if both of these things are on the stack, then we do things the old way. Otherwise, we only need one temporary. Oh, we also need to say we only need one temporary going forward here. Now, this block doesn't return a state. So we kind of forget what happened inside of a block. I guess that's kind of okay. I guess. we'll roll with that for now. When we call this recursively, we just need to be careful because it kind of invalidates whatever we were doing with registers. And that's fine, we can work with that. So we'll say let r0 equal. So the first register we work with, if, let's call it reg adder. So if let expression, so if, expression destination, right? So we know in this case, either one or the other or none of these ended up on the stack. So if it's a register, then we just give back that register. Otherwise, we need to get a temporary register. So we're going to say state get temp. And yeah, we'll do it with the temporary. We'll just return that. So we either get a register or a temporary. And we're going to have this same thing. If let, hold on, I missed an equals here, equals res adder dot destination. Oh, a couple of bots to quickly ban from my chat. Timeout and ban. Timeout. That one is banned. We will timeout and ban the other one. Wonderful, wonderful. Get rid of them. Put them in the bin. Okay, so equals res adder dot destination equals res value dot destination. So the registers associated with this thing, and then we write value like this, we say hey, but we use R0, we use reg adder and reg value. Okay, so what happens if I make this test now? Well, it crashes because, of course it did. Register found, yep, I need to unwrap here. That is good, and here as well, unwrap. Excellent. Well, that passes now, but it still fails, probably for the same reason. So let's have a look at the generated code and see if this will disappear, but this will still be here, but I think this will disappear. Or at least it will disappear if it can allocate registers to do things. And it's okay with them just being in temporaries. It's okay. Don't worry about it. Just don't worry. So this is still here. But as I think I said, the B and the C, where it's like pop B, pop C, that is gone. So that's good. We are reusing some registers. We still have this issue though, where we load an immediate into a register that has just had this stuff happen. So what could this mean? What could this mean? What's this first line, right? It's when we do this thing, right? We get the address, the left-hand side. No, hold on. It's when we compile because assign array, we have a left-hand side and an index. So it's the left-hand side of this part. So left-hand side index add. So what this means is within this binary operation, we're loading the left-hand side, which is here. And then we push it, I guess. I don't know why we would pop it straight away. I don't know why we would need to pop it straight away. Unless we're trying to put it on the stack to operate with. But then why does the index... Also, that's not the index. What is this? Where does the number 2 come from? What happened here? Where did this go so wrong? Where did the number 2 come from? Because we're doing this multiplication, right? AAC. So it thinks we're multiplying something else. I'm doing this add as well. It thinks we're doing something very different here. Well, not very different, but so what are we saying? We're saying multiply A by C and add that result to A. Let's check in add. Deref, because it's a pointer, we're doing this multiply, right? This is part of the pointer logic. If we look at our code gen expression, if I look at variable, I think it's going to be this code gen expression deref. So this, we're not doing this at all. Literal int, that's cool. This is going to be a problem when we get to it. Built-in size of, that's fine. No, it's not. This really isn't fine. We need a free register for this. We need to say well, okay, we can leave size of as well. That's kind of okay. I suspect, so address of has this problem, function call, we resolved it. We probably don't want to do this too. Oh no, well, we do. We always return on the stack, which is kind of weird. I thought we did kind of fix that. Anyway. I thought I did stop this always happening. Why is this after the jump? Hold on. This is a rogue instruction. Let's see if we can find a PC jump. When do we... MPC 0. Yeah, okay. That's not quite what I thought it would do. Okay, anyway, I'm getting distracted. When we have a variable which is a collection of fields, so this does struct fields as well. This is where we have the, here. So, okay, we get a temporary. It always goes on the stack, so that would explain why we have a push and then a pop. It wouldn't explain why we then load an immediate directly into C. It's because, actually, wait, is this using a temporary? It is. Let's just say get free. Oh, but it's on the stack. That's actually fine. It's what we're popping it into is using a temporary. So when we're doing the bin op, okay, so anywhere that says temp, I'm suspicious. Instructions clone, we have two expressions. That is okay. We pass the state through, which is good. Do we touch the state? Yes. Okay, so this is supposed to be res rhs.state. No, it's supposed to be res lhs.state. We're supposed to thread this state through. Now, I don't think this needs a clone. Because this is in a match. So it should be res lh. Actually, instead of this, I'm just going to do what I did before and say let state equal res lhs state. I'm going to move it here. And I think that's going to work. I think that's going to work well. Okay, if I clone here, then I should be able to get rid of the clones here. And then I can't balance my brackets properly. Okay. We hit bad memory, but that's okay. Heap. I don't think my heap has this address anymore, does it? Left equals right failed. Let's recompile. Let's see what it does now. We should be a little bit more aware now. Push, and we still get this immediate. I still don't know why we get a number 2, right? So what does this even do? So B0, so this is the index, right? So why do we ever load the number 2? We push it. So this is the start of the chain. So then we're adding. We should be adding this with 0, right? We should be adding this with 0, then dereferencing it. So we compile the left-hand side, which is B, the address of B plus 0. So we've got the address of B in the C register. And it looks like it now knows that it should be using... So it's just this one frickin' instruction. So where do we have an immediate? We have an immediate here. RT. Size. Interesting. So why are we using C here? How does this end up happening? Why are we popping into C? Get temp. Down here, we also call get temp. Could it be something to do with this? Probably. So are we in this branch, right? Get temp pair 0 T0 T1. Yes. Swap? No, we don't swap though. So we're not in that branch. So we've compiled. So this is the left-hand side and this is the right-hand side. Right? So compile, but the left-hand side. Oh, hold on. We compile the left-hand side. Yeah, that's right. So we compile the left-hand side. The left-hand side is the address, right? So the left-hand side is the address of this thing. Why is this hard? Why? What have I done? the address is the left-hand side. We compile the left-hand side first. That makes sense. We also don't need to clone the state anymore. We shouldn't, because we should be using a later state always. Move occurs, okay. Oh, that's actually okay, because we have to clone because this is in a loop. So that's a nice little way we could check for ownership, but that's not gonna cut it, unfortunately. Okay, so, so the problem is that something is picking a bad register out of the hat, right? It's trying to get two registers to work with. For some reason, it's picking register C twice, but then immediately after, it's actually trying to do the right thing and juggle B and A. So it's trying to step by the size of the type, right? It's trying to say, actually, hold on. Oh, wait, no. So this is right. So B, so we're multiplying B by C, right? So this is the offset that we're trying to add to. And we're trying to add it to the thing in C and put it in B. But, and then this is correct. And then we push C. This isn't correct. Why do we push 17? Like this is fine, actually. This is a kind of a no-op, I guess. As long as we don't need to pop, as long as we don't expect to pop that value, which I think we don't. So there's an unnecessary push, but that's okay. But we store, and so we should have, as if we hadn't have just overridden the correct address, or the correct value rather. Load word. Yeah, so we've loaded the value, which is an address in itself. We're then trying to add 2 times B to this, right? So we're doing this multiplication. So when we do the binary operation, the left-hand side is a variable. Okay, so this is what we're doing. So we have a field. We get the type. We get the aha. Here's the culprit. Okay, so we have a temporary. Can we abuse this temporary to do 2 things? Or do we need to get the temporary pair? That's also allowed. Can we, actually, I don't know if that is allowed. This is a tricky one. Okay, so what we want, stack field offset. Get stack field offset. This is defined in util, right? This is where we like the field offset, get the offset within this thing. Target register. So it's a local, so we are going to load word target register 0. Yes, this is why. Okay, so actually the problem is this bit. This bit doesn't tell us that we've just consumed a register. So, okay. So what we need to do is say let offset, let field offset reg equal state get free unwrap. And this can probably break in a whole bunch of ways. This is unsound. This will crash sometimes. But now instead of this, we use field offset reg. And now anywhere we had register C before, I'm not exactly sure where register C went. Like what are we expecting from this? Where do we use this again? Load by. Does something else assume register C in this chain? No, maybe not. So we're loading from T0 to T0. Oh, hold on. So we're loading from this. So actually, this should be a temp. This, yes. Okay, so we're gonna use T0 here, T0, and then we do this, and then we push it, this is going to be the same thing. This is going to have the same problem, but it's technically more correct. System C0, that's the end of our program. B0, push, pop. Okay. So up until here, we're behaving ourselves. This worked because we'd hard-coded register C. It worked because register C is our temporary variable, so this was kind of the same thing, but this is more correct. So immediately after this, the binary operation starts, and for some reason... Actually, no, the deref starts. The deref comes first, does it? No, the binary operation does happen. The binary operation happens because if we're doing this on a pointer, we have other special logic. If it's a pointer, we do this stuff. So are these on the stack? Are these both on the stack? I don't think so. I think only one is. Yeah, it must be, because we don't see the swap. Okay. So we have two registers. RT is the temporary, but these are already the temporary. So we only need this. RT is only used if it's a pointer. So we need two, oh, this is such a freaking mess. We need two registers if and only if this is, this is really rough. If this is a pointer, we need a register pair. So I don't want to fork this logic and copy and paste it. What we're going to do is we're going to say, and this is going to cut into our savings quite a lot, require temporaries. We're going to need two temporaries, okay? We're going to let T0 and T1 equal state get temp pair, unwrap. Instead of this, we're going to say R equals T0. Actually, we're just going to hard code this to T0. Whereas here, we're going to just hard code this to T0. So one of these two branches is going to be T0. And then we'll call this other one RT. And then RT doesn't need to exist anymore. Cool. Okay. Except this doesn't work if R0 is... no. We need another thing. We need another variable. We're going to make a mutable thing called register. We'll say reg out, and we'll call it register 0, which should be just really invalid. If this is okay, then we're going to say reg out equals R. And if this is okay, we're going to say reg out equals R. Right? So we're going to remember one or either of these is the destination. And actually, I'm going to put an extra check in here, which I hate. If reg out is not register 0, then do this. So we'll try and use R0 because that's the left-hand side. And we'll call this reg out. Does R1 get used? Okay, we do this. Okay, this is gonna fix it, kind of. Require reserve temporaries. And we don't need to do that. I've been writing JavaScript, so I've been having to put parentheses in places where I don't like to put them. Did this fix it? No, but it broke it in a different way. That was a different error, so that's good. Always getting a different error is indistinguishable to progress. That's a very wise programmer taught me that. Okay. So we set this up, we save it, we load the index that we're working with, we load the, here we go, this is different. So let's zoom out a little so we can see our registers. We load the, the local variable into C, and then we swap it into A, so that then when we load the size of the type into C, we put the stride, right? So the size of the thing in the array multiplied by the index of the array, B times C. We then add this into B. We push it to the stack, which is unnecessary. We then save into address B the value in A. So we write 17, so that's correct. And this memory is read-only because my machine's not set up to handle this address. What memory setup do I have? I think my console should tell me. What do we have? Heap. Oh, hold on, the heap is baked in. The heap is baked in. Wait, hold on. Why don't I heap? What do I need? Let's just put a heap at here and let's make it really big. Okay, really big heap. That's too small. That was not enough things. Oh, hold on, wait, that's also not the right syntax. That's assembly syntax, not C-like syntax. Where is this set? Where is this set? Bin leng. Was right. If this is now a little bit out of date, res to binary, result is the result of compile. Compile, we make a context, new, function definitions. Do I just not define a heap? What heap? What's my heap? What it says in here, right? It says in here. I have a heap. The address is 100. The size is this. How big is this? Oops. Hex 32,760. I feel like this is a number I should know. Hex 8,000, and it starts at 112, which is 70. So that should be fine. Why is this address not okay? Hold on. Let's tick back to where it broke. It was the store word. It was this. So B is a very sensible address. B is a very sensible address. But, oh, the memory's read-only. That's really strange. Why is this mapped as read-only? Size 112, address 0. That's also fine. Heap also has a file offset 0, that's fine. So, this should start right after... Why is my heap read-only? That's a bit of a problem. It's a bit of a huge problem. So this is good. So we're using the stack a lot less, right? That's kind of the key of this. And this is only because some of my code doesn't even try to not use the stack, right? We're doing this swap, but it's good that we're doing this swap. And this is so much cleaner. Like this used to take a lot of instructions. And actually, let's have a quick look. So let me go into my thing, and I'm just gonna disable the reuse. If I make them all temporaries, that's kind of like turning this optimization off, right? So if I do this, so this was 110 lines. If I do this now, still 110 lines, because that didn't actually change anything. That's weird. I should have changed something, right? Maybe. C-A-B. I guess because of this. We were doing more pushes and pops before. Oh, I guess we're not, because these are real simple. Okay, anyway. That was a bit of a non-starter. Once we fix this, then that will cause some savings. Excellent. Okay. Okay. So what actually goes wrong in the test, I guess? Like what happens? So we say that array instruct I don't really care about. Array return I do care more about. This panics. Memories read only. Oh, is the address supposed to go on the left-hand side? Hold on. VM source R1 R2 base page. Oh, hold on. Store word. Where are we? Let me reload this with those optimizations on, because the registers used are a little bit different. Store word BA. So B is the... Sorry, the value is meant to be on the left. So wherever we have that store word, and that should actually be in the code gen block store word, store right value. We're putting these in backwards. Array return memories read only. Okay, so that would be the correct error. Stack push pop. Oh, and that actually we have to do it here. Okay, sorry, so here it was right, but here the value goes first, then the address. There we go. Now it should look a little different. Wow, and that actually fixed both tests. Beautiful. Okay, that's good. Let's commit that real quick while we're popping. Cargo format. Lang source compile. Deref statement uses registers. Cool. So where's this push? What was pushing here? This was the actual deref. Something was always pushing, right? One of these expressions. Several of these expressions, like string literal is, literal char is, and literal char should be really easy to fix. But anyway, built-in size of. Deref. Deref is always returning on the stack. We would like deref to not always return on the stack. But I don't think that's the specific thing that was causing this. So deref's returning on the stack, address of is returning on the stack, function call is returning on the stack. Variable, this is the one. So variable we'd want to return not on the stack if possible. So we have a temp, and this is good. And then we want to say, actually, what we want to do here is say, let reg is temp. So we want to have a little block here, and I'm going to put a block, right? We're going to do a couple of things. So if let sum r, so if we can get a register from the state that is free, then that's good. We'll return r true, r false, sorry, otherwise, and so then I can get rid of a whole layer of indirection here. What goes on here? Otherwise we give back state get temp unwrap true. Cool. Okay, so T0 is out. T0's out of favor. This is now called reg. Excellent. And now, if is temp, so if it's a temporary, we do this, we push it, and we return it on the stack. Otherwise, we don't want to do that. We want to say, okay, expr res from instructions. We want to give back out, we want to give back state, and we want to say that this is in a register reg. We also want to say reg dot reg dot set. We want to say it's got a variable in it. And that variable is going to be, I guess, whatever concatenating fields is. So we'll say fields dot join dot, I think. Add a semicolon here, yes. Add a semicolon here, yes. That is supposed to be state. We're modifying the state. Vec join. Okay, do I have to clone it first? Perhaps. Vec unsatisfied. Identifier. That's not ideal, is it? Let's maybe say fields first. No, that's not right either. We have to map these things to their underlying strings. Then we're going to collect it into a vec. And then we are going to join on the character dot. So we get the name in some degree. That's better. That's much better. Cool, so we're doing that transformation, that works. Expected register found string. Got my arguments backwards, that's okay. Move occurs, so we need to clone it. State cannot borrow as mutable because it's not mutable, that is fine. State, where is our state? Where does our state come from? Our state gets passed in, right? State, we're just gonna say that it is mutable, because that's easy fix. Result that must be used, we will ignore it. Wonderful. Okay, so now if I compile this, load it in and run it, we should hopefully see that that strange load and move is gone and our code is the same length. So we still push and pop. So I guess we just ran out of registers, but at least we know that in theory we could jimmy it around that. And so what goes on? So let's look at 16, B, shift left, C, immediate, store word. So we save it there, we get a, let's see, load word, and then we do this move still, which is annoying. We shouldn't need to push them pop here at all. We still push. Why do we push? See, load word C0. Load word, so it's where we have this, right? Where we load, because we've saved it and that's fine. Now we load it. Stack. So load word. So why is this a temp? Why can't we get a free variable? Because we've used B and we've used A. That checks out. That checks out pretty well, actually. All right, well, so that's good to know, right? Like, our optimizations do not fire at unjust times. Okay, our optimizations are sensible. They show some restraint. The other things, so if I make T right now, what do we see? Other things fail. Array instruct fails. Hold on. Did I just break array instruct? Because I had it fixed before. Would be nice if I could see which instruction was just being executed. A, B, C. So, oh gosh, that's actually, yeah, that's very wrong. That's very, very wrong. Weird. So we're obviously in this branch, right? Because something has changed. Oh, hold on. Well, the thing went, oh no, we're setting it to a variable. We're setting it to a variable. That's okay. Don't panic. Don't panic. What? I guess it would be worth checking to see what happens. Like we have an actual result type here, right? A register state error. So let's maybe try to return this out. Map error, and it's a compiler error register state E, and we'll question mark this up. Okay, well that's good. So we don't have a bad register state. That makes me happy. We've ended up with a real dud value in a register. So let's load the array instruct test memory lang tests. It'll be instruct array. No, it won't. Lang tests array. Sorry, array instruct. We'll grab this. See, globals I haven't really thought about. We'll jump into my file test2. We will paste all this in and compile and run from here. Let's look at the assembly that this generates. Cool, so let's start ticking through. 164 instructions, that's still not too much. The main function here is really not where I expected it, which is kind of weird. Oh, well, they get compiled in order. That's fine, that's fine. So main starts down here. 2 locals, sorry, out and... Oh no, sorry. We're here. Mhead and foo, that makes sense. No, sorry, just foo, but foo is bigger. Foo has extra things, that makes sense. So we load this address and we store it at this magic address, which is cool. Put 100 into B, because we're about to call, because this line does nothing. This is all taken care of when we allocate space in our stack frame. So this line in the program is kind of a no-op. We're about to load 0 so that we can call malloc. We have to push that, of course. We set up a stack frame. We jump into malloc. Malloc out equals mhead. Mhead, so this is the global offset. So we just loaded the global mhead into A, that's the hex value 1000, that's correct. We now want to set up our local variable, which again, we should be able to do some static analysis and say we don't actually need to store this necessarily. Oh no, we do, sorry, we store this because well, no, we don't need to store this, but we need to add something to mhead as well. So we're storing this first. We then load AC0, load word BB0. So we get the value, we get the argument rather. And so we're doing this sum. We have to do this load again, which is a bit unfortunate. We do the add. So A still has the old value of mhead, B has the new value of mhead, C is about to get the address of it. I don't know if this is quite correct. I think we're missing something in between here, but that's okay. Yeah, we might break if we have more than one global, so that's worth keeping an eye on. B base pointer 0. So we load the base pointer into B. We add an immediate into B, so we're getting the first local. So we load this again. We move it into A. So this moves into A because we return in A. So we do this without the stack, which is good. So this is somewhere where we have an obvious saving as of, you know, the state of the compiler last week. Now, we set up to return. Nice. So we go back to where we called from. ASP, we push the result onto the stack. So we got this result, we push it onto the stack. Oh yeah, because that's the result of the function call. Yes. So this always happens. This always gets pushed. Now we're gonna get, we add a couple of things to C. C is the base pointer. We get an offset to that, the offset of the field LMs, which is at offset 2, so that's correct. That is correct. We add 2. We then pop into B. So B is now the address of the memory we allocated, and then we override it immediately. And then we do something. Okay, we went a bit off the chain. I might have to call it there for tonight, unfortunately, but this is an obvious place to work from, and we will keep smashing through this very, very soon. Thank you very much for tuning in. Bit of a quiet, bit of a chill stream tonight. I am Tom, and I will catch you next time. Thank you to everyone following along. Good night.